Recording is rolling. Today is Wednesday, September 21st. Okay, and I'm going to do as many college physics textbook problems as I can with you guys today. You guys remember this page here? These are all from chapter 4. Yeah, chapter 4 in your book. Okay. All right, so a couple things before I do that. I had a faculty meeting this morning, and do you guys remember this whole plan about like you're supposed to each get a laptop? Right, from school, right? So new program we're doing. So about October 28th, Friday, October 28th, you guys are we're supposed to like take the whole day, and then yeah, whole day to you guys are like supposed to like watch videos and go through like some process and get laptops, and it's gonna be a whole day thing going on there. Yeah, so that'll be thing. All right, now let's do this. Let me okay, hold on. I have to connect the screen thing. Still getting used to the system here. All right, connect. All right. So you guys remember that PowerPoint we've been looking at last couple of days with free body diagrams? Right. They were just a few slides right at the tail end. So want to. Oh, okay, we're good. All right. Let's try this again. Share screen 2. All right. All right. Here we go. Yeah, let's look at the last few slides. So the last one you guys saw yesterday was a block on an incline. So it's definitely got a weight. If it doesn't have weight, if it's just like floating around in space, then you don't have anything else. So you got to have that. Okay. Then what I told you guys to do was to introduce a coordinate system that runs parallel or perpendicular to the surface. You guys remember that? Okay. Now this is a process question. It's good to see this a few times. You guys saw it yesterday. You're going to get a nice review right here. Okay. And this is going to be something you have to do. Right. Now that weight is not aligned to that coordinate system. By the way, why do I like that coordinate system? I like that coordinate system because that block is the motion of the block is constrained along the surface, right? It can move along, say, this dashed line axis right here. Okay. So we're going to have to represent the weight in terms of that coordinate system. Okay. See, like the weight, it's partially pushing the block into the incline, but it's partially trying to make the block slide along the incline. Okay. So we need component vectors, component of mg. And the two components, boom, there they are, the cosine and sine components. That angle is that angle, right? If that's 28 degrees, that's 28 degrees, right? Okay. And notice the right angle and the right triangle is where the components come together, right? Okay. Do you guys see how this sine component down here is parallel to the surface, right? See how it's parallel to the surface? Can you guys make parallel lines like that, right? All right, and then see there's a normal force, which is exactly opposite of the mg cosine theta. Right? In fact, if there's nothing else fancy going on, it's equivalent magnitude to just mg cosine theta. It's called that. Okay. All right. Now, if I stop right there, if I stop the free body diagram, would that block be at rest? No, there would be a net force on it. What would the net force be equivalent to? Mg sine theta, exactly. Right. So these two purple dashed components are replacing the mg. Right. So you can just like scratch out the mg. Okay. Yeah. And then the mg cosine theta and the normal force cancel out. Okay. And there is a net force, and it is mg sine theta. In fact, that would be the free body diagram for your Hot Wheels car rolling down the incline, wouldn't it? Right. Put little wheels on the block, zoom, accelerate down. Right. But if it's at rest is an example of equilibrium. So I need one more force, which is the what force? Friction. And friction is going to point which way? Exactly. Bam. Right there. Okay. You know what? One last little thing on this. Suppose I did not give you any of that white text, and you only had the free body diagram. You open up textbook, you see that free body diagram, no other context. Okay. You guys see there are really 3 forces, right? The weight down, the normal force, and the friction force. Right? You don't know anything else. Right? Now you do see that the friction force is equivalent magnitude to this component mg sine theta. Okay, so you figure that out. Okay. Now, if I didn't tell you the block was at rest, would you know for sure necessarily that was the case? The block was at rest. You guys are right. The answer is no. What other thing could the block possibly be doing? Moving at a constant velocity, because that would also be a case of equilibrium, wouldn't it? Right? Remember, free body diagram. If it's an equilibrium, all the forces are balanced, and that might mean at rest, but that might also mean moving at constant velocity, right? And then it'd be ambiguous as to which one of those is, right? Now, if it is truly at rest, we're talking about static friction, right, versus kinetic friction. Okay? So hold on to this idea, because next week I'll have you guys do a friction lab. It's going to come back. All right. Oh, but let's do these real fast. The block's sliding kind of down the incline. It's basically going to look the same, isn't it? Right. Okay, so it's the exact same free body diagram, right? And that would be a constant speed. Okay? You guys just told me that. It's the exact same free body diagram, except it's kinetic friction instead of static. Okay. Right. And then, what if the block is sliding up the incline? Now, this one actually is going to be a little bit different. What's the one thing that's going to be different? Yeah. Boom. The direction of the friction changes. Remember, drag force, friction force is always opposite of the motion, right? Well, in this case, like there are two surfaces sliding past each other, and friction always opposes that motion. Okay, so boom, 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 boom. Those are all the same so far. And then the friction changes direction. Okay, now that block right there, is that block in equilibrium? Definitely not. Right? What's the net force? I'm thinking this mg sine theta is pointing kind of down the incline. And also, so is the friction force. They're both conspiring together to slow down that block in a hurry. Think that block is slowing down in a hurry, right? It has a huge net force on it. It's got this force plus this component, right? Right. Atwood. So tomorrow, your guys' lab is going to be this Atwood. So let's do a free body diagram. Now, if AP asked you a free body diagram question on an Atwood, what I've always seen them do is just pick one of these two masses, say like M2, and just have you guys do the free body diagram of that. But let's do a free body diagram for like each of those masses. Okay. Now, each of those masses, did they each have a weight? Right? They each have a weight, right? Looks like, okay, so that'd be proportional to the mass, right? So if it's like triple the mass, it's triple the weight. So we got that, those different size vectors going on. Okay. Now, from a macro point of view, from a systems point of view, those are really the forces that you care about. I mean, maybe you're holding that pulley in place, like with your hand, but if I'm saying like what's accelerating the two masses, those are like the external forces, right? They each have a weight, right? Now, are there more forces involved? Yeah. Do you think there's a tension in the string? Right. And if I'm focused like on a micro point of view, if I just zoom in on either one of those masses, then each mass has two forces on it, right? It's weight and a tension, right? I'm trying to change my own convention to F sub T for tension force because capital T sometimes used for time period, but this presentation is a couple of years old, so capital T I was using that. Right? Sometimes you see that too. All right. Hey, how many tensions can one string have in it usually? One tension per string. Right now, maybe you can make a case if there's some friction in this pulley that might go out the window, but let's say it's a frictionless pulley, frictionless massless pulley. Right there you go. There's only one tension in that string. It's the same tension. Right? Do you guys see that M2 has a net force downward and that M1 has a net force upward? You guys see that? Because I think that whole system's going to go counterclockwise. You guys think counterclockwise? It's going to be accelerating, isn't it? With the net force, right? Is that? So that's a setup to solve this. Now you could ask some different questions about this. You could say, what's the downward acceleration of M2? You could say, what's the upward acceleration of M1? By the way, do you think it's the same acceleration? Yeah, because they're tied together with the same string, so they have the same motion, right? Just one's going up, one's going down. Okay. You could ask, what's the tension in the string? In fact, I think one of your textbook questions asked like those questions, right? Sometimes I just say, what's the acceleration of the system? And you guys get the idea. Just right. All right. Oh, and you know what? If you wanted to like do total overkill on this, I don't think I've ever really seen this come up. But you know, if you want to say, hey, what's the forces on that pulley? Well, that pulley has a couple of tensions down, and maybe like the pulley itself would be in equilibrium, wouldn't it? It's not accelerating up or down, right? So the forces have to balance, and that's how you could balance the forces, right? Oh, let's think about some different scenarios. Let's go to extreme boundary conditions for setting up one of these Atwoods, right? You guys get to take out these materials and get them in your hands tomorrow, right? What if these two masses are exactly the same? Exactly the same. Let's say they're each 1 kilogram, right? Could you imagine that first of all, is the system going to be accelerating? No, it's just going to probably be at rest. If it's moving, it'll be just constant velocity, right? It's probably just be at rest, right? And then do you think the tension would be equal to the weight of either one of the blocks, right? So 1 kilogram, 10 newtons, 1 kilogram, 10 newtons. The tension would also be 10 newtons. If you have a 10 newton weight here, 10 newton weight here, the tension is also 10 newtons. That would balance everything out, right? And then how much force would you be holding up with? Like 20 newtons, right? Which kind of makes sense. You have to hold the full weight. Okay. Now that's if everything's just sitting at rest. What if you do this though? What if you do the other extreme boundary condition? And this thought process we're in the middle of doing right now, like extreme boundary conditions. This is something I picked up from my engineering classes in college. Like if you're trying to work your way around, how does the system work? I think, well, what if I take these variables to certain extremes, right? Then sometimes you can frame the problem, right? So the other extreme thing you could do is you could put all the weight on one side and have an empty string on the other side. Wouldn't that be the case? Okay. And then wouldn't all the weight just be in perfect free fall, just 100% free fall, 100% of gravity, right? 10 meters per second squared straight down. And what do you think the tension in the string would be in that case? Pretty well zero, right? if it's just an empty string on one side. Okay. If there's zero tension, do you think you need very much force to hold it up? No, you barely feel, you probably wouldn't even feel it, right? It'd just be like it's just a free fall doing its own thing. Right. Okay. All right. And then this modified Atwood is a oh well, I didn't put the word modified up here, but that's what AP calls it. AP calls it a modified Atwood. Okay. So when I have you guys do this, I might have you guys slip a little Hot Wheels car in here just to remove most of the friction. And then, how's this going to look like? We'll do this one real fast, but you guys can think about that. So I bet the weight of M1 hanging over the edge is the only force that's providing the driving force. Okay. Now, there's still a tension force internal to the system. Oh, that's what I meant to mention too on the last slide, but I can mention it on this one. Okay. Guys, this tension force that's just holding everything together, is that an external force that's driving the system to move, or is that just holding everything together? It's just holding everything together, right? If I take this ink pen and I just like start accelerating this ink pen around, there's an external force from my hand moving the ink pen, right? But there's a bunch of like forces like holding the plastic parts together. Well, that's not driving the system move from an external point of view. That's just holding the system together, right? Okay. Same thing with this tension. This tension is not an external force. So in the macro sense, when you're trying to figure out how things accelerate, the way I approach is just ignore the tension because it just holds everything together. Okay? Now this block on top, this M2, sure it has a weight, but that's being balanced out by the normal force. Okay? Now there might be a friction force that would affect motion, but suppose it's either frictionless tabletop, like an air hockey puck up here, or if you slip a Hot Wheels car into there, you pretty well get rid of the friction. It would look pretty much exactly like that, right? Okay. Now this M2, I don't think there's an external force that drives anything to move because, well, they're two that cancel out, right? The weight and the normal force, right? But this M2 does have a bunch of inertia, doesn't it? Right? If M2 is, if you make it bigger, right, it's going to slow the system down just because it's adding inertia to the system, right? Right? You guys kind of get that? Okay. So yeah, I'm giving you guys a bunch of hints as when you guys do this lab tomorrow, right, how to frame these Atwood problems. All right, let's knock back over here and solve as many of these as we can. All right, so you know what I think I'll do is I'll just pick the same problems that I assigned you guys, but I'll just change the numbers. So yeah, and if you want to go an extra step, a good thing you'd be able to do is to solve in terms of variables too, right? So number 2, a football punter accelerates a football from rest to a speed of, I'll change the speed, okay, during a time that is toes in contact with the ball, which is, ooh, look at that, a fraction of a second. By the way, that interval time looks familiar. That looks like, you guys remember dropping the rollers, your reaction time was about that, fraction of a second. Okay. If the football has a mass of this many kilograms, what average force does the punter exert on the ball? Okay. So the way they give you this setup is there's just enough information where you can answer that question. Okay. So number 2, got ourselves a football. Right. We're gonna put a force on the football, kick it. Now I'll try to stick to the conventional free body diagram, which is we have put center mass of the football and forget this ruler right here. Right. Let's say I kick it off with some force. Remember the way you draw forces is you're gonna connect the tail of the force vector to the center mass and then extend the force vector away from the center. Right. That's the only way AP accepts answers. And actually, I like that convention myself. So I'm doing that for all my classes. Okay. I'll call this force. Okay. Oh, by the way, that's what we're solving for. Notice this says average force, because if you really want to get granular, right, you say, well, if you break it down like nanosecond per nanosecond, and make contact with the ball, then pushes against it, and eventually the ball leaves his foot. Maybe I'll make a graph with you guys, but there's some like average force that makes all these numbers come together. This football has a mass. What else we got? Oh, we got a final velocity. Okay, so when the football leaves his foot, it's going at some speed. So maybe I'll say like maybe the initial could be 0 meters per second, and there's also some speed built up to. I'll call it VF, like a final velocity, right? Minus sort of kinematic stuff. Okay. Oh, and then there's a time interval of that force. Okay, because could you guys imagine if you if his foot is in contact with the football for like twice as long, if that force is acting twice as long, right, it's going to accelerate the football for even more, and it's going to speed up even more, something like that. So there's some I'm going to say delta t for time interval. Okay, so time interval. Sometimes they'll just say t. Sometimes delta t, like a change in time, like a time interval. You see that? Okay. Right. So we got all these things going on. Okay. No, I could tag number C's. In fact, I'll just leave the mass of the football as what they say here. I don't know. Does anybody know? Is that actually accurate? Is mass of football half a kilogram? I don't know. Let's run with it because that might be the case. I don't know. Okay. I'm gonna have a force of. I'm gonna do. Oh, whoops! Actually, that's what we're solving for. Solving for the force. Okay. I'll say. Let's say there's a final velocity of. I'll do 18 meters per second. Why not? Okay. And I'm gonna have my time interval as being. Well, they went 0.2 seconds. Maybe I'll go 0.25 seconds, something like that. Okay. So a little bit longer interval of time, but also faster speed than the book gives you. Right? Is that right? Now, this you can set up starting with Newton's second law of motion. Second law of motion. Okay. Maybe just in terms of variables and then in terms of the numbers, right? You guys remember force equals mass times acceleration, right? Or acceleration is a net force divided by mass, right? There's really a net force, right? A net force. Okay. But let's just consider like kicking force, maybe ignore the weight of the football. Simplify this a little bit, right? Now, acceleration. Guys, what's the definition of acceleration? Going back a few weeks ago? Rate change of velocity, right? Rate change of velocity. How fast is the velocity changing? Okay. So I'm going to modify this and say mass times change in velocity per unit time interval. Right? Okay. And then, you know what? This is actually one step away from the impulse formula, which is going to come back about a month from now when we're studying momentum and collisions, because there's like a collision going on here. I'll just point out right now. Here, I'll put it in parentheses, but this is like taking a side path. We're not going to go down. If you cross multiply this t force for some time interval, that will cause a mass to change its velocity. Right? Okay. So this is going to come back when we get to momentum and collisions. You guys are going to see this. It's called impulse. Right? Now, we're not quite going that way, but that's right. Okay. So in terms of the number, actually, this is pretty well the answer in terms of variables, isn't it? Maybe I can do this. Force equals mass times change of velocity is not final minus initial velocity, okay? Which initial velocity was just 0. So minus 0, whatever. All divided by the time interval. Okay, that's the answer in terms of variables. Okay. Once you have that, it's real straightforward because I guess you just pop in the numbers, right? Okay, so let's pop in the numbers. So force equals the mass of the football. We got the right, final speed was, okay, I went with this number of meters per second. Your book number is different. Going from rest. And then the time interval of this many seconds. Okay. I didn't change the numbers very much from their book, so our answers shouldn't be wildly different. Okay. Here we go. Right. Of course, you guys have these solutions posted anyway online, so you have access to those. Okay, but I'm looking at this many newtons. Okay, now really that's a net average force is what that represents. Okay. Net force because I guess if I wanted to get crazy with this problem, I could consider, well, what about the weight of the football? And the force has to also overcome that. Blah, 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 right. So it's a little bit simplified, but got that. Okay. And then, what about the whole deal with average? Okay. You guys good so far? Is that all right? Okay. Right, so let me draw you guys a graph that's eventually going to come back in this class. Again, especially when we get to like momentum and collisions a few weeks from now. Okay. So suppose we're tracking the force as a function of time. Okay. Now this guy's foot is in contact with the ball for a tiny fraction of a second, right? So we're talking about like 0.2 seconds total. Okay. What's kind of a more realistic version of this curve? Well, it's going to look like this. At time 0, his foot is just making contact with the ball, so there's 0 force to start with, and it starts pushing against the football. See if you did like an animation of like, let's do like a few frames on this football. Here's the football. Okay. Okay. So then his foot makes contact, and then it pushes a little bit more, then pushes a little bit more, and then the football starts to leave his foot, and then in the last frame it finally leaves his foot, and there's no force again. Okay. So it's like the force is going to build up, right, and then it's going to come back down. Okay. Okay, so if you have like some kind of like accelerometer on the football or some kind of force sensor, it would be a graph that looks like that. Now, what you guys just solved for is like is the average force. Now, this point right here might be F max. Where do you think F average is on this graph? Yeah, right in the middle. Yeah, F average. Right, that's what we just found. Right, like if there's like an average force. Okay, you guys just solved for that, and I got like 36 newtons. Right. Right. And why am I making a deal about that? Oh, but by the way, here's another perspective on why that would be average. Right. If you're in calculus someday, you'll do average value, and basically this. What if this is an iceberg and you let all the ice melt? Right? Isn't it going to just melt down to that line? It's like they have the same area underneath them. Okay, this is one way to think of it. Because what if this football is like made out of some material where it can withstand up to 45 newtons, and if it's beyond 45 newtons, the seams are going to break. It's all going to crack apart. Okay, you solve this whole problem and get 36 newtons. Okay, looks like I'm in the clear. But wait. You go up to 45 newtons. I got 36. Is that football safe? Because what's the max force on the football?
72.
72. 72. So it looks like the seams are going to break. Right? You guys get that? Right? Because you have to take average force of 36 newtons and double it to get the maximum force, which happened for. Okay. All right. So we got fourth mass acceleration. We've got Newton's second law of motion going on there. A 75 kilogram man, this number 7, 75 kilogram man standing on a scale, in an elevator. Note that as the elevator rises, the scale reads, more than his usual weight. Because guys, if you're 75 kilograms at the surface of Earth, you should really weigh about 750 newtons, right? N times G. Okay. But if you weigh more than that, you must be accelerating up in the elevator. Oh, what is the upward acceleration of the elevator? So should I tell you guys too, you guys know I've been hanging posters from my ceiling. I made a new poster for you guys last night that's basically these notes I'm gonna write right here. Okay, so got ourselves an elevator. This guy right here, okay, standing on this scale. Okay. Now it well here, I'll do some terms of variables first like I normally do, and then just plug in some numbers later. Okay. The guy's at center of mass. Right? There might be a couple of forces on this guy. He's got a weight, which is mg straight down. Okay. Now, suppose the elevator's not moving. Is there a normal force from the scale that's pushing up? Okay. So call this F sub n. Right? And if the elevator's not moving, then would these two forces be equal in magnitude? Yeah. Okay. What about this? What if the elevator is moving up, but it's moving up at constant speed? Would that be the exact same free body diagram that these forces cancel out? Yes, it would. Yes, it would. Remember, guys, constant velocity is also a case of equilibrium, right? As if you're standing still. You guys remember that from in a moving car, it's cruise control. It's like as if you're at rest. Right? So if the scale's rating higher than its usual weight, the elevator has to be accelerating up. Right? It's either going up faster, or the elevator is moving down, slowing to a stop. Either of those would work, right? So I'll do F sub n, like the normal force reading from the scale. That's really what the scale is reading, right? Your normal force, right? The normal force. Okay. Right. So I'm going to say that the net force, F net, is the normal force up minus the weight down. Can that be true? The net force. Okay. And do you guys remember from Newton's second law of motion? What's net force equal to? Mass times acceleration. F equals ma, right? So I'll make a little substitution right there. Leave this part the same. Normal force minus the weight. Okay. Okay. I think the question was what's the acceleration of the elevator, right? So with that, right? Let's go that way with this one. Right? What's the acceleration of the elevator? Right? You guys can see what it would be in terms of variables, right? Right. I guess you could plug in numbers whenever you want to, but this is a good skill to have in AP physics to be able to solve in terms of variables. It's whatever the scale rating is. Mine is his weight at rest or in equilibrium. Okay. All divided by his mass. That's one way to solve it. Let me pop in some numbers. Let's suppose suppose his mass was like 60 kilograms. Okay, so we got 60 times 10 would be about 600 newtons. I'm rounding a little bit here. Okay, but what's the scale reading was showing like 700 newtons. 700 newtons. Right? So say I've got a net force of 100 newtons acting on 60 kilograms. I would be getting an upward acceleration of 1.67 meters per second squared. Oh, and I'd have to specify upward too, right? So it'd be upward. Okay. Right, all right. Guys good there? Okay. Actually, I want to take this a little bit different way that's going to help you out for a number of problems that you guys are going to see in the future. Okay, so let me start this out the same way. Well, almost. All right, but I want to do something a little different. Okay. Let's just look at the elevator. Okay. And then what if there's like a, okay, we're just look at the whole elevator. Okay. This elevator has a weight, I'll say like mg. Okay. And maybe there's like a cable pulling the elevator up and it has some tension. I'll do F sub T for a tension force. Right. It looks pretty similar to what we just did, right? Instead of a normal force from a scale, now it's just a tension in the cable pulling it up. Okay. Okay. So the net force is equal to, in this case, the tension force minus the weight of the whole elevator. Okay. And I'll start exactly the same way as I just did it. Mass times acceleration then would be tension minus the weight. Okay. But here's where I'm gonna divert from what I did before. I'm gonna take a different path through the force and solve for something different. What if I want to know what is the tension in this in this elevator cable? I wonder what that is. And I did know what the acceleration was. Okay. See, that's kind of opposite of what we just did. We said if you know the normal force reading, what's the acceleration? But what if you know the acceleration? You want to solve for either normal force reading on the scale or the tension in the elevator cable. Right? Right. You just solve this a little bit different. Can I just do a little algebra switch around right here and say that the tension reading is going to be mg plus ma? Would that be true? Right. Oh, and then m is equal to m, so I could factor that out. Would that be the tension is going to be m times g plus a? Right. Now that's true if the elevator is accelerating which way, upward or downward? Clearly upward, because I have the upward force is greater than the downward force, right? So the way I solve this is specific to accelerating upward. If accelerating upward, that's true. Okay. Now I could start from scratch and just make the weight greater than the tension force. Kids go back to being balanced, right? What if they're all balanced, right? You put a little slack in that elevator cable. Is the elevator going to accelerate downward? Yeah, right? Right. And check it through the steps. What do you think the one small difference would be at the very end? It's not going to be exactly this. What's going to be the one difference? Instead of a plus, it's going to be a minus, right? Because imagine this. What if you did? Let's take this to an extreme case. Let's do that boundary condition. What if you cut the cable, go, and elevator goes into pure free fall, all the way down? So in that case, the tension would be zero, wouldn't it? Right. So how do you make this zero? Hey, you could do g minus g because it would be accelerating down at a rate of g, wouldn't it? Right. So more generally, I'll say the tension force in an elevator cable is equal to m times g plus or minus a. Right. This is one of those expressions that's good to have in your back pocket because this is going to come up a few times later in the semester. You'll see this every once in a while on FRQs, sometimes some multiple choice questions. This is a handy formula to have. Okay. Now, I should tell you guys too, though, that if you see the scenario on an FRQ, they will expect you to derive the whole thing. So they'll want you to start from the first step and then go through this process and then come to this conclusion, right? But, you know, it's good to know what the conclusion is to be able to pull it out of your back pocket and solve a multiple choice question real fast. Okay. Guys good? Tension in an elevator cable. All right. Guys ready for number 10? 5-gram bullet. Pause right there, because if you're ever given grams and you're applying physics formulas that involve like newtons of force, you know you're going to have to convert to what first? Kilograms. How do you go from grams to kilograms? Divide by 1,000, right? Because kilo is 1,000. At least the muzzle of a rifle with a speed of hundreds of meters per second. What force is exerted on the bullet while it's traveling down the barrel? Oh, and they give you the length of the barrel of the rifle. Right? I think we're gonna have to combine a couple of parts of physics here. So here, maybe I'll start kind of from the end, and I think we're gonna be missing some information. Okay. So they asked, what's the force? You know the mass of the bullet. Only you can get the acceleration. right? Because you know this number, check, you're solving for this. Okay. If only you knew the acceleration, or, hey, could we go back a unit to all the kinematic stuff and say, well, see if the bullet starts from rest and it picks up to this velocity in this distance, that's 3 kinematic values, isn't it? Ooh, right? Now, notice they didn't say anything about how much time the bullet was going for, you know, there was a time interval, right? But since you know that, which kinematic formula is going to allow you to solve for acceleration? First, second, or third? Okay, I like the third one because you know it starts from rest, you know what speed it builds up to, and you know the length of the barrel. So boom, 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 that's 3 things. Okay. Now, if you wanted to, you could do a roundabout way. You could, hold on a minute. Well, I guess you could use system equations for the first 2, but that would be really convoluted process. So I like the third one. Yeah. So if you pick one of the first 2, you'll just end up with like several unknowns and this is really hard to solve. So go back and do this. So this guy right here, I got final velocity squared equals initial velocity squared plus 2ax. Okay. You guys are able to visualize what's going on, right? We got whatever rifle looks like, something like that. Okay. This bullet going from here to here, okay, starts at v naught is 0 meters per second, travels this distance x, and then has some v final coming out the end of the rifle, right? And once it leaves the end of the rifle, it's no longer under the force of that explosion, right? Okay. Now suppose the force is constant all the way across, right? Okay, you guys got that? Right, so I'm gonna make up my own numbers. Let's say it gets up to like 500 meters per second. Don't forget to square that. Come from 0. Trying to figure out what's the acceleration. And I know I'm gonna think my rifle is like let's say this many meters long. Just come up with a number. Okay. Can you guys do a little algebra and solve for the acceleration of the rifle? Okay. I'll do it myself for my numbers. You guys have different numbers. So let's see, square this. Okay. And then divide by 2x. So divide by open parenthesis, all that stuff. Okay. I'm getting a couple algebra steps later. Oh boy, that's a crazy big acceleration. So something kind of like that. Okay. Actually, since that's a middle step, I might want to keep more significant figures, but it's gonna be there. Okay. Then I'm gonna take that number. Remember, that's just part 1. That's not what they were asking for. Right. I gotta pop that in right up there so that I actually can solve for what was asked for. Okay. So now we're back to our classic Newton's second law of motion, F equals ma. Okay. I'm going to go force equals, I need the mass of a bullet. Right. Remember, you're going to take the number in grams and divide by 1,000 to get to kilograms. So that's going to look something kind of like something like this, for example. Okay. And it had to have been accelerating this much to have reached the given speed in this given distance, right? That we did that before, that was right. Took care of that already. That's how we got this number. Okay. So that many kilograms times that many meters per second squared. Here's the force on my bullet, that many newtons. Okay. Right. Is able to follow that process? Is that right? Okay. Any question? Any question? Okay. And so, I'm seeing a lot of F equals ma show this as a framework to solve these problems so far. Okay. A boat moving through the water with 2 forces acting on it. We got a 2,000 Newton forward push by the water on the propeller. So the propeller is pushing against the water is pushing the boat forward. Okay. And an 1,800 Newton resistive force due to water on the bow. What is the acceleration of the 1,000 kilogram boat? And then there's some follow-up questions like how far it's going to go in this time interval and what's its velocity going to be, which sounds like a kinematic type question. So we'll take your time here, right? So, let's do a free body diagram sort of for this boat. Okay, so I got a boat, the water, the center mass. Okay, get some. Let's have mass. They told you Subject that, I'll keep the mass the same, about 1,000 kilograms. That's a nice round number. Okay, so if it's 1,000 kilogram boat, should the weight be, what's the weight in newtons? About 10,000 newtons, right? And then the buoyant force would have to exactly balance that out anyway. Right, so we're going to ignore all the vertical forces, right? We don't really care about those. Okay. I do care about the horizontal forces because those are different. Okay. So I've got the propelling force and the drag force. Okay. So F propel equals, I'm going to make up my own numbers. I'm going to go with this many newtons. Let's say F drag is like, I don't know, maybe like half that or something. Nah, I should do it. Here, let's do 1,600 about that. All right, it's got 3,000 newtons propelling and 1,600 newtons drag. Okay. All right, guys got that? Got 4 forces. Okay. Now, again, the 2 verticals are going to cancel, so I can just ignore those, whatever. Okay. But the net force then is going to come from these 2 horizontal forces. Okay. So F net is F propel minus F drag. Which looks like, if I just pop in some numbers, that many newtons minus that many newtons. Okay. Okay, so now I got a net force on the boat. Okay. Oh, and if you know the net force and you know the mass of the boat, do you solve for the acceleration? We're back to the second law of motion. Right? So mass times acceleration of the boat, that's what net force is, mass times acceleration. Okay, is 1,400 newtons. Okay. So if I do 1,000 kilogram boat, giving some acceleration by this force. Okay. I really like the fraction form of Newton's second law of motion. Maybe I should have started from that. Acceleration is net force divided by mass. Right? Because that's really where this is headed, right? There is a net force, there is a mass that's causing some acceleration. Okay. So last step, divide the mass down, and looks like my acceleration is going to be that by 1,000, this many meters per second squared forward through the water. So got a boat speeding up through the water at that rate. Okay. You guys got that? Okay, so I should write that down, adjusting that. Okay. They told you the mass of the boat and a propelling force and a drag force. So the difference between the propelling force and drag force is the net force. The net force is just mass times acceleration. Okay. And then now you have 2 of 3 things. You know the net force because you just took the difference of those 2. And you know the mass because they gave it to you. Divide this 2, pop, pop, get the acceleration. Boom, boom, done. You guys see acceleration is kind of a bridge between the first 2 units, right? Unit 1 was kinematic motion. And that was where we had these three amigos. And then unit 2 is forces, dynamics, we get Newton's second law of motion, F equals ma, the whole deal. Right? Oh, and that also involves acceleration. So acceleration looks like a bridge between those 2 units. Okay. Speaking of which, we're going to take that bridge over to kinematic motion. Because they asked you guys, if the boat starts from rest, how far will it move, and how fast will it be moving at the end of some time interval? So I'm going to use this tax BV checklist. Okay, so they told you the boat starts from rest, which means this number is 0 meters per second. Okay. We just did a bunch of work to figure out what the acceleration is. I got this number, which is different from your book numbers, so some version of this, right? Meters per second squared. Okay. And finally, they told you time interval. They said so many seconds go by. So maybe like this many seconds, for example. Again, changing the numbers a little bit. Okay. And look at the 2 questions they asked. They said, how far does the boat move? And how fast does it pick up to? Boom, boom. That's the 2 questions they could have asked, right? That's that. So I'm thinking to answer the X question, how far does it go? I'm just going to go V naught T, which is just going to be 0 anyway, plus 1/2 AT squared. And solve it that way. Okay. If you want to figure out how fast it picks up to, go V final equals V initial, which is 0, plus AT, which is just, of course, AT. So. Right. Guys can solve that? Then that answers all the questions. Right? Guys good there? Okay, she's got a question. All right, so that's those four. Nice little warm up there. Ooh, I like this one. The bird food. So we got a bird feeder. They told you, notice they told you the weight of the bird feeder, which is kind of nice. They could have said mass, you'd have to multiply by gravity. They went ahead and just straight up gave you the weight in newtons. Okay? It's supported by 3 cables. And they gave some angles here. Ooh, do you guys see a 30, 60, 90 triangle? Okay. You think some trigonometry is about to pop up? We're about to break out sine and cosine, SOHCAHTOA. And that is one of these special rectangles too. So maybe that's kind of nice because you guys know one of those ratios, like sine of 30 degrees is exactly 1/2. So that might help us out maybe along the way. We're gonna find out. Find the tension in each cable. Tension in each cable. Well, I can get one without doing any work at all, right? Because I see 3 cables, right? There's one straight down and one up to the left, one up to the right. Okay. Do you guys think the one straight down is just going to match the weight of the bird feeder itself? Yeah, so boom, we've got one out of the way and I didn't even write anything, right? You know, the one hanging straight down is just the weight of the bird feeder. Boom, boom, done. Okay. But what about the ones that are going up to the left, up to the right? Okay. Let's blow this up a little bit. It's number 19. Okay. So what I'm gonna do is pick this point right in the middle where all the ropes come together. Okay. I'm gonna do a free body diagram at that point where all the ropes come together. By the way, if you're doing civil engineering in college, there's a whole class you'll take called statics, which just solves a bunch of problems like this, basically. Okay. Let me introduce a Cartesian system that runs parallel perpendicular to gravity. Okay. And then have those big forces. Okay. So I know one force is the weight of the bird feeder straight down, which is also the tension in that downward rope. Okay. Now, they told you 150 newtons. Just to give you guys an extra example, you guys can try this yourselves. Maybe I'll change mine to, say, how about 250 newtons? How about that? 250 newtons. That's what I got. And they've got one rope headed up this, say, 60 degrees to the horizontal. So kind of like I'm trying to get this right here. Let's try this. I think it'll be pretty close. Right, one rope that way. Now they said that this angle right here is 60 degrees. Well, they drew it in a different place, but that would be equivalent to that angle there, wouldn't it? Okay. And then see, there's another one. It's going this way, like 30 degrees. Okay. I'm going to draw that one kind of short, and you guys will see why as this plays out. Okay, so this right here is a 30-degree angle. Okay, is that okay so far? You guys can look at the setup, right, and then translate it to like this free body diagram. Right, so we're looking at the point where all the ropes come together. Okay, is that right? All right, so this bird feeder would be in equilibrium, which means that all the forces balance out. Right? And I've already introduced the Cartesian system, which is going to be the framework to help solve this, because we're going to say what's going on in the x direction and in the y direction. Remember, equilibrium. For us right now, that means that the sum of the forces is equal to 0 newtons, right? And then, well, we've got like 2 dimensions. We got vertical and horizontal. So I'll modify this a little bit by saying the sum of the forces in the x direction and the sum of the forces in the y direction are each 0, right? And then later on, probably closer to December, January, we're going to add one more condition for equilibrium, which is that the sum of the torque is equal to 0. Every time you open a door, there's that turning moment. Great. We're going to take that for a few months from now. But for now, we're just focused on the forces. Okay. Okay. Right. I think I need some components. You guys want to do some components? So let's break these each into XY components. Now you can go up and over, or you can go over and up. It doesn't matter which way you do it, but I'm going to go over and up. because I think it's gonna play out a little bit better on the paper. Okay, notice I'm dashing these components. Okay, now AP, whenever you solve free response questions for AP, this is just like right here. If you make these components solid, they will take off points. And the reason they'll do that is because you're like double counting the vectors. You're saying these vectors, there's even more ropes point. No. Okay. But if you dash them, then they'll probably like let it go. They'll probably let it slide because they're like, okay, well, you're just dashing them, so you're specifying their components. Okay. You either want to draw the components or at least be able to imagine the components being there. Okay, so there's the side components and there's the up components. Like I said. All right, now remember I made the one kind of going to the right kind of short, and I said there was a reason I was going to do that. Okay, here's why. You guys see the rightward component and the leftward component exactly balanced? That would have to be the case, wouldn't it? Okay, this one pulls right as much as this one pulls left. You see that? The only way for that to happen is this tension has to be less than this tension, right? So these two balance. Okay, that satisfies this right here. Some of the forces in the x zeroes out. Is that true? Okay, and then in the y direction, do you guys see that this little bit up plus this big bit up matches this amount down? Look at that. That plus that is going to balance out with this. That satisfies this condition. So the forces zero out vertically. Guys see that? Yeah. All right, you guys ready? Oh, I need to put some numbers in here. Oh wait, no, we don't. We don't know what these forces are. Let me label this T for tension, and I'll do subscript L for left. And this will be tension on the right side. So you got tension on the left side and tension on the right side. All right, you guys get that? Can you guys break those into? See, we need some components, right? So I'm gonna call this T left times sine of 60 degrees, right? Just like square root 3/2. I'm going to call this T left times cosine of 60 degrees, which turns out to be exactly 1/2, right? Half of TL. Okay. This is going to be tension on the right side times cosine of 30 degrees, which is like square root 3/2 from a math class. Okay. And this is going to be tension on the right side times sine of 30 degrees, which conveniently is a 1/2 ratio. Okay, guys remember that? Okay, so now we're gonna set up those these expressions here, right? These conditions, right? In a way that you can already see visually, right? And that's why I pointed out these cancel out, and these two up have to balance with this one down. Okay, we're gonna write that out, and then you guys see we're gonna have two unknowns. Do you think we're gonna have two equations with two unknowns? These are going to set up the two equations, and the two unknowns are what are each of the tensions. You guys see where this is going? Right? See how it's going to work? Okay. Got a few seconds to the bell. All right. Well, got as far as I can today, but I would like to finish this one, so I'll see what I can do for the rest of the week. But yeah, you guys have the solutions posted to Google Classroom anyway, right? So you guys got this there? All right. Any questions? All right, you guys have a great rest of your day, and I will see you tomorrow. The plan tomorrow is Atwood Lab. Oh yeah.